Hello. We will be solving this sample problem using the double integration method. So what is required for this problem is to provide the general moment, slope, and elastic curve equations. Um, I will be solving this problem using in three ways, just to show you the different ways that we can actually solve this problem. The first way The first solution is we would not be extending the distributed loading. And we would be using the leftmost end as x is equal to 0 and the rightmost end as x is equal to 5. We have to note that um, you could actually solve this problem by not extending the distributed loading because the distributed loading extends up to the rightmost end of the beam already. If it does not extend to the rightmost end of the beam, that's the time that you have to extend the distributed loading. Okay, so I already solved for the supports at the fixed support, the support reactions. So you have a 30 kilonewton upwards load and then a 40 kilonewton meter counterclockwise moment. However, since we would be using the rightmost section here, we would be sectioning the beam over here. We do not really need the value for the support reactions since we would be considering the beam from the leftmost end up to this section. Okay, so here is the section. As you can see, we have now a trapezoidal load because we have cut the beam just before x is equal to 5. So for this trapezoidal load, since we would be getting the moment equation, we would be dividing the trapezoidal load into a rectangular load whose height is 20 minus 20 over 3 times x minus 2, and then a triangular load whose height is 20 over 3 times x minus 2. Again, what we did to get this height is to do our similar triangle. So for our similar triangles, the large triangle has a height of 20 and a base of 3. And then this would be the lower height of your trapezoid, which I labeled as h. So again, the base from the trapezoid, the height of 20 to h is x minus 2, whereas the base from h up to the uh, height of 0 for the triangle is 5 minus x. Now, we note that I use this triangle here, this one. So, that triangle has a height of 20 minus h here and a base of x minus 2. And by using similar triangles, we have illustration proportion with 20 over 3. Hence, h would become 20 minus 20 over 3 times x minus 2. Now, I know some of you would actually try to use this triangle here, this one, because it's kind of easier in a way to view this triangle. So the height of the triangle is h and the base is 5 minus x. If you use that triangle, h or h prime, I labeled this as h prime because it has a different notation, would be 20 over 3 times 5 minus x. Now, why do we not use this representation? We use this one. So the problem with this representation is, once we create our moment equation, the base of the trapezoid of the triangle is x minus 2. So if you get an equation of 20 over 3 times 5 minus x times x minus 2, you would be having a hard time integrating the equation. So let's say you get uh, I'm having a hard time using the pen. So just imagine you have to integrate 20 over 3 times 5 minus x times x minus 2. So what would you have to do? You would have to uh, multiply 5 minus x times x minus 2, and that kind of nullifies the effect of your discontinuity function. Okay, so do not, again, I repeat, do not use this representation, this one. Do not use this representation. We use this one, this one. Okay, so here we go back to our beam, and we now create our moment equations. First, of course, you have your clockwise moment, 100 kilonewton meter. So again, if you are using the left side of the section, clockwise moment gives you a positive bending moment. So 100 times x minus 1, because your 100 kilonewton meter applied moment is located at x is equal to 1, but you have to raise it to 0 for your applied moment. And then for your trapezoid, for the rectangular part of your trapezoid, that's the height is 20 minus 20 over 3 times x minus 2. And then the base is x minus 2, and you have to multiply it by the moment arm x minus 2 over 2. And then for the triangular part, the height is 20 over 3 times x minus 2. And then base x minus 2, we divide it by 2, base times height over 2. And note that if your triangle is positioned this way, the moment arm of the centroid is actually 2/3 of x minus 2 and not just x minus 2 over 3. So again, reminding you, we do not use this notation because what will happen, we would see an equation 20 over 3 times 5 minus x times x minus 2 times x minus 2. So you would have a hard time integrating that. You again, you cannot simplify this equation by doing x minus 2 cube and expanding that, because the discontinuity function will be rendered useless if you do that. Okay. So here is the moment equation, and I would simplify that further because it's quite long, and this would be the simplified equation. So just note that negative 20 here times x minus 2 squared over 2, this would be where this came from. And then this is positive 20 over 3 times x minus 2 squared over 2. You would actually have two terms with x minus 2 over 3, and this would be the simplification of those two terms. Then, to get EI theta, or the equation for the slope, we integrate this equation once here. This is the integral, and don't forget the arbitrary constant, C1. And then, you integrate it twice, and here you get C1x plus C2. Again, do not forget this part. And after you have integrated the equation twice to get EIY, what you have to do is to solve for C1 and C2. Now, for our beam, if you remember, it has a fixed support at the rightmost end that pertains to x is equal to 5. So, at x is equal to 5, you have a fixed support, and at the fixed support, you have first y is 0, and then the slope is 0. Remember that. For the pin and the roller support, only y is 0, but if you have a fixed support, the slope of the elastic curve is also 0. What you have to do is to substitute those to the two equations. X is equal to 5 to the two equations. First, use the equation for slope so that you can solve for C1, and you get C1, negative 332.5 kilonewton meter squared. And then, substitute x is equal to 5 to the second equation, EIY, and substitute the C1 that you got from the first equation. You will now get C2, 916.5 kilonewton meter. So, to get the equation for the slope and the deflection, you just substitute C1 and C2 into the equation. Now, the second solution, we can actually solve this problem by extending the beam. So, this is actually optional, but it would kind of make an easier solution because you would not be dealing with a trapezoid. So that's how the solution becomes easier. So again, I have here the section diagram. You still have the trapezoid here. So how do we extend the trapezoid? We make it into a rectangle. So that's how you extend the trapezoid. Now, to make the trapezoid a rectangle, you actually added a triangular load. So again, to balance out the additional load that you made, here is the balancing load. So at this point, the height is 0. So the height at this point should be 0 as well. And then this height here should be the same height as this. Now, you don't have to compute for that actual height. So what would be the height of this triangle? First, the height of this rectangular load, now rectangular load, is 20 kilonewtons because the height at this part is 20 kilonewtons. And then, how will you get the height of the triangle? I already told you in class, the shortcut of getting the height, it would just be the slope times the base. So again, the slope of this triangle still came from the original triangle. That would be 20 over 3, and then the base is x minus 2. So here, the height of this triangle is 20 over 3 times x minus 2. Okay? So now, we can make the moment equation. Again, for this clockwise moment, that's 100 times x minus 1 raised to 0. And then for the rectangular load, it creates a counterclockwise moment about the section. So that gives you a negative bending moment. 20 times x minus 2 times the moment arm, x minus 2 over 2. And then for the triangular load, the upward force creates a clockwise moment about the section. So you have a positive bending moment due to that. You have 20 over 3 times x minus 2. This is the height. And then base x minus 2 over 2. And then the moment arm x minus 2 over 3. There. So actually, if you would look back to the solution 1, the moment equation for the solution 1, the simplification of that equation is actually the same as this equation that we have here. If you would remember the simplified equation from the solution 1, this is actually the same. Since this is the same, integrating the equation would yield you the same equation with the same C1 and the same C2, since you have the same equation. Okay? There. Now, the third equation for the third solution, I will just show you because we haven't discussed this in class and I just mentioned it in passing. You can extend the load to the left. You can extend the load up to the left and then section at the left side of the beam. Now, I told you in class that you can have two representations you can still set x is equal to 0 to be at the leftmost part of the beam. So if you do that, this should be 5 minus x. However, what I will show you is x is equal to 0 would be at the rightmost end of the beam. Here, this is x is equal to 0. So that would be one of the differences from the solutions that I have shown. This rightmost end would be x is equal to 0 and the leftmost end would be x is equal to 5. Now, if you do this solution, you would now need the values for the reaction, the supports, 30 kilonewton and 40 kilonewton meter. Of course, for this problem, it would be a tedious solution. The other two solutions that I showed you would be easier solutions. But I just did this solution just so you could see how you go about extending the beam to the leftmost end. Okay? So how do you extend the beam to the leftmost end? So you make a large triangle. And in doing so, you have actually added a trapezoidal loop. It's downwards. So again, you have to balance out the trapezoidal load that you added by adding a upward trapezoidal load with the same height, lower height, and higher height. Now, again, if you extend your load here, you have to consider the whole triangle. Do not extend the load and then just consider the smaller triangle and then the trapezoid. So again, the shortcut that I have taught you, the slope, again, it's 20 over 3 for the same triangle times the base. That would be the height of this large triangle. So the base is x. Now for the trapezoid, the height of the rectangular part of the trapezoid is 20. So here, the height of this arrow is actually 20. And then the height of the triangle, here, the height of this triangle is 20 over 3 times x minus 3. Again, still the same shortcut. The slope of the triangle is 20 over 3. And then the base is now x, this whole thing, from this end, from the rightmost end of the beam up to the section is x. And then this length here, up to here, this one, is actually 3 there. So the remaining length of the beam is x minus 3. Okay? So now the moment equation, now since we are now using the right side of the section and we are summing moment at this point here, the convention would now reverse. So the forces that would cause a counterclockwise moment about the section, again, we are summing moment here at the section. The forces that would cause a counterclockwise moment about the section would now give you the positive bending moment. And then the forces that would cause a clockwise movement about the section would give you a negative bending moment. So here, for this 30 kilonewton, here, the 30 kilonewton load, it would cause a counterclockwise moment about the section. So you have 30 times x positive. And then the applied moment here is counterclockwise. So it would give you again a positive bending moment. 40 times x raised to 0. You could actually omit the x raised to 0 here. However, I just placed it in the equation so that you would just be used to multiplying distance raised to 0 for the applied moment. Okay. And then for the triangle above the beam that is downwards, the height is 20 over 3x, base is x divided by 2, and then the moment arm is x over 3. The negative bending moment, this gives a negative bending moment because it gives you a clockwise movement about the section. Then for the trapezoid, the rectangular part of the trapezoid has a height of 20, base x minus 3, and then moment arm x minus 3 over 2. Again, note the positive sign because it gives you a counterclockwise movement about the section. Then the triangular part, height 20 over 3 times x minus 3, base x minus 3 over 2, and then moment arm x minus 3 over 3. Again, positive sign because it gives you a counterclockwise moment about the section. Lastly, your clockwise moment here is now negative 100 times x minus 4 raised to 0. Okay, so what we have to do next is to integrate this twice to get uh, the equation for the slope and the equation for the deflection. Now, we have to note that x is equal to 0 pertains to the rightmost end of the beam now. This is the difference from the other solutions. So, reminder, if we're going to solve now for C1 and C2, which you will see in the succeeding slide, you would be substituting x is equal to 0 to the equations, not x is equal to 5. So, let's do that. Here is the moment equation. And then, here is the equation for the slope. Again, you integrate it once, and then integrating the moment equation twice gives you the deflection equation. So I already simplified the equations as I integrated them. Now, the fixed support is at the rightmost end. Since the rightmost end is now our x is equal to 0, there, you substitute x is equal to 0 to the two equations to get where EIY is 0 and EI theta is 0. So, doing so, for EI theta, so there, you see the zeros. And then here, 0 minus 3. So, again, that cancels out. That's 0. Here also, this is 0. And then this is also 0. And, well, you get C1 to be 0. So, that's the difference from the other two solutions. The arbitrary constant values are different. And then, you also do that for EIY. So, again, this becomes 0, this 2, this last one, and C2 is 0. So, the difference from the two solutions, for the first and second solution, you don't have to solve for the support, but you have a value for C1 and C2. For this third solution, you have to solve for the support, but your C1 and C2 are both 0 because you have a fixed support at the rightmost end. Now, I want you to see that even if we got a different equation for the three solutions, well, the first and the second solution have the same equation, but the third is not the same, the C1 and the C2 is not the same, we should be getting the same values for EIY and EI theta. Although here I will just show you the value for EIY. So for the first and second solution, our equation for EIY is this one. And then I will just get the EIY 2 meters from the left end. So 2 meters to the right of the left end. So for the first and second solution, that pertains to x is equal to 2. We substitute that to this equation and we get 301.5 kilonewton meter cube. Now for the third solution, this is our equation for EIY, quite different from the equation for the first and second solution. We would be getting the EIY at the same point, 2 meters from the left end. However, again, I reiterate, you would have to substitute x is equal to 3 to this equation because x is equal to 0 is at the rightmost end. Okay? And what would you get? You would get the same value, 301.5 kilonewton meter cube. So, different equations, same value. Okay? So, that's how you extend to the left. That's what you do. Okay? So, I hope you would understand these solutions that I have posted. And you can just ask questions and message me if you have any questions for this tutorial. Thank you.